So I'm here to present some work that has been undertaken by the research and development team at Equinix. Originally, Ted Hardie was going to be here as well, but he's currently recovering from emergency appendectomy surgery. I have to move this. I am not an Equinix employee as such. I did this work under contract with them. So, I'm going to start off with the assertion that the slash dot effect is a distributed denial of service attack. And most of you probably know what I'm talking about when I say slash dot effect. This is when your little web server suddenly becomes very popular because it got listed on Slashdot or mentioned on the national news, or from a few years ago it became the cool side of the day. And something like this has a tendency to melt your network, overwhelm your server. Possibly it can get bad enough that it prevents you from performing maintenance tasks on your network. You wouldn't even be able to log in and shut down the server, reconfigure the server, or whatever. If your network that is experiencing this problem is hosting other content from other customers, then it's a denial of service for them as well, and this is a real problem. In the introduction this morning, John talked about the newspaper here in New Mexico that received 8 million hits in one day. This is the kind of thing we're talking about, where all of a sudden you weren't really planning on having a lot of people visit your website, but it happens. So what's something we can do about this? One way to address it is to move the popular content closer to your network border. So keep the traffic off the internal network, keep those links uncongested, and try to serve the popular content right at the edge of your network. This slide has a word that you may not be familiar with called surrogate. This talk is about what we call a demand-driven surrogate. First, let's talk about what a surrogate is. This text is from some pending IETF legislation. So a surrogate is an intermediary program which acts as a server or a tunnel for the purpose of responding to requests on behalf of one or more origin servers. Requests are serviced internally from a cache or by tunneling them on to the origin servers. Surrogates are also traditionally known as reverse proxies or server accelerators. So, no, really, what is a surrogate? A surrogate is much like a proxy cache, except that proxies act on behalf of users, while surrogates act on behalf of origin servers or content providers. A surrogate is any sort of network element that acts like a server but may not be the authoritative source. So a mirror site is a pre-populated surrogate. Content delivery networks such as Akamai, Adero, etc. may provide surrogate services. The demand-driven surrogate is a system that can be activated only when popularity overloads the origin server or its network. So this is an important point. This is what this talk is about, is activating something only when you need it and only for the amount of time that you need it. This thing that we're calling Bellwether is based on a number of open source components. So we use Squid for caching, we use Zebra for routing, we use FreeBSD for some IP firewall features, and the surrogate also configures the IP firewall rules to divert new HTTP connections to the Squid process. The existing TCP connections and non-HTTP traffic are routed normally by the surrogate over the GRE tunnel. So this is an important thing to keep in mind. If the origin server is doing things besides HTTP, if it's handling mail and DNS, then there's going to be a fair amount of other traffic going through the surrogate, although simply routing packets is not a huge overhead for it. It's not going to kill performance. Another important thing to note is the IP firewall in FreeBSD has some neat features where it keeps per connection state. So we can turn it on and only divert the new connections, and any connections that were established prior to that are handled just via routing. And similarly, when we turn it off, new connections are sent, just routed over the GRE tunnel, not sent to squid, but the connections that were already being sent to squid continue to go that way. After it's been activated, squid creates a cache of the popular content for the origin server, and any cache misses are just tunneled over the GRE tunnel. That's redundant. So cache hits are served from squid, keeping a lot of the content off of the busy network and reducing the load on the origin server. That's the basic plan. Now I'm going to talk about some simulations that we did to convince ourselves that it works and that it works reasonably well. We created a little test network with about 5 systems and made the origin server have some bottleneck. So in this case, we configured its network interface to be 10 base T, while all of the other systems were 100 base T. And we created a workload of about 9 hours worth of traffic. For the first hour, it starts off low at about 5 requests per second, and then suddenly it increases to 100 requests per second. Given that the origin server has a 10 base T network, with this workload, it should be able to handle about 50 requests per second. So we're really pumping in a lot more requests than it can handle. The load stays high for about 2 hours, and then it trails off over the next 4 hours and continues on even a little bit after that. The ideal hit ratio for this workload was 90%, which is certainly reasonable for an origin server with a nice, relatively small collection of content. The hardware for this is not anything really very fancy. This is a 33 megahertz Pentium 2 with 512 megabytes of RAM and a couple of SCSI disks. So here's two results, 2 graphs. The red one, I don't know if you can tell that's red, is the case without the surrogate. And the blue is the case with the surrogate. On the y-axis, we have response time on a logarithmic scale. At the bottom is 100 milliseconds, here's 1 second, and here's 10 seconds. And the x-axis is the duration of the test, about 9 hours. So in the case without the surrogate, when the request rate increases, the response time increases as well to a very unreasonable amount, 10 seconds. That's way, way too long to wait for any web page, any response. And it stays this way for most of the plateau and then back down. Contrast that with the surrogate case where it stays nice and flat, something like 200 milliseconds for the whole test. The logarithmic scale on this graph shows an interesting feature where, at this point, the case without the surrogate actually has better response time, right? So this sort of shows that there is an overhead to pay for using the surrogate. It's not always going to be better. In this area here, this is when you would want to turn the surrogate off and continue sending packets via the normal route. So 100 requests per second is pretty good, but it's not spectacular. We wanted to prove to ourselves that we could handle higher request rates. So we used some beefier hardware. This is this next result is from a dual Pentium Xeon 550 system with 2 gigabytes of RAM and 10 SCSI disks. As you'll see, the peak throughput here is actually about 480 requests per second, which on this axis corresponds to 48 megabits per second as well. This is a workload that we like to call a boiling frog. So over a very long period of time, 18 or 17 hours, we slowly increase the request rate. It starts out at about 390, and it keeps going until we see something break. So that break happened here, and we got up to about 480 requests per second. Next steps for this project include improving some error handling that we've seen. In the case that the surrogate gets overloaded, we want to start to bypass the surrogate and send some of the requests onto the origin server. So essentially we're doing now load balancing between the two. In the event that squid should fail, we intend to withdraw the route announcement, and the border router would then forward the packets on the normal way. We plan to use the network element control protocol to signal between the origin server and the surrogate, or to signal between whatever else might have knowledge of the fact that something bad is happening, that the network is melting. We intend to make a prototype implementation with Apache, and we're very interested in exploring integration with layer 4 switches or layer 7 switches from some of the vendors. We have some questions for you. In your networks, when you see CNN events, etc., popularity spikes, what is it that breaks or melts? What breaks first? And related to that is, what sort of devices or processes in the network would need to signal the surrogate to kick in and start serving the content from the border? We have some code that you can pick up and play with. It's certainly not to the state where you should use it in a production environment, but we're hoping people will read it, look at it, test it out, and you can get it from that URL there. There's a mailing list hosted at Equinix for the discussion of surrogates in general. You're more than welcome to subscribe to that and bring up some issues or ideas. And if you have any questions for myself or Ted Hardie, those are our email addresses down there. And that's all I have, except for questions.
Do you have a mechanism to handle multiple proxies? Instead of scaling by machine, scaling to multiple proxy surrogates?
So to have multiple proxies hanging off of one border router? We haven't tried it. Offhand, I don't see a reason why you couldn't put a load balancing switch in front of the surrogates.
Right, so you'd use traditional load balancing techniques there.
Yeah.
And then obviously the problem nowadays is there's a huge swing towards dynamic content, as well as the problem of rapid expiry. How do you handle cache expiry? Just simply go and whack the squid cache, or?
To answer your first question about dynamic content, if your origin server is serving a lot of dynamic content, then this is not the greatest solution, right? This is not going to help a lot. If your content is expiring quickly, there's two ways to approach that. You could sort of leave it as it is and let the surrogate refresh at the normal rate that it's supposed to. Also, since the surrogate is really the origin server moved somewhere else, you could say tweak the surrogate to cheat with the expiration times. Say, well, I know that it's really supposed to expire every 5 minutes, but since I'm dying, I'm going to keep it for an hour, something like that.
And finally, is there a mechanism for giving the surrogate kind of preferential treatment to go and fetch the data from the content server? Or once you've kicked the rerouting in, are you saying that no future fresh requests will go through at all? So in fact, the surrogate is the only server hitting the content server?
There's no way to really guarantee that the surrogate would be the only thing hitting the origin server, especially if you have multiple border routers coming into your network. In that case, what I didn't talk about is you could have multiple surrogates, one at each border. But even then, there's probably no way to guarantee it. Does that answer the question?
Yeah.
Okay.
Thanks, Duane.
Bill's got a question.
I'll talk to you about this later. This frightens me.
Okay.